On page 301, we need to talk about coordinate proof. Now, coordinate proof is a little different beast than what we've been doing. It's where we put a figure, and we're going to be dealing with triangles for now, on a coordinate plane and use coordinates to help us prove things. Now, the strange thing about it, though, is even though we're using coordinates, we're very rarely using numbers. We're usually going to use letters as our coordinates. And our letters will be constants. So instead of having a point, with coordinates 2, 3, maybe our coordinate, or maybe the coordinates at that point are B, C. But B and C aren't variable. They're constant. We don't even need to know what they are, other than to know that they're constant. So we're going to take learning how to do coordinate proofs in small steps. And our step for today is to position and label a triangle for use in a coordinate proof. So we're going to be able to be given a description of a triangle and place it on a coordinate plane in such a way that the coordinates will make sense to us. We're going to be given a drawing of a triangle on a coordinate plane and be given some of the coordinates and figure out all of the other ones. And if we can do that, then we'll have mastered this learning target. Now, something you need to know about isosceles triangles. The altitude, and the altitude of a triangle is a segment that starts at a vertex and is perpendicular to the opposite side. So all triangles have altitudes. Okay? So an altitude starts at a vertex and is perpendicular to the opposite side. We call the length of the altitude the height. So quite often we'll use height and altitude interchangeably. Technically they're not. The altitude is the segment. The height is the length of that segment. But, we'll be okay. We'll use height and altitude pretty much interchangeably, and we'll understand what we're talking about. Now, in just a general triangle, all right, let's one like this. If I draw the altitude from that vertex, now that altitude's obviously, the altitude, no matter what, is going to be perpendicular to the opposite side. That's the definition of altitude. Starts at a vertex, goes perpendicular to the opposite side. But in the blue triangle, that altitude obviously does not bisect that side, does it? But in an isosceles triangle, it will. And in the blue triangle, that altitude does not bisect this angle up here. But in an isosceles triangle, it will. Okay? In an isosceles triangle, the altitude is considered to be, there's actually 3, but the altitude of an isosceles triangle starts at the vertex of the isosceles triangle. Remember what that is? The non-base angle. The 2 base angles are the congruent ones. The vertex angle is the one where the legs join. So we're going to consider the altitude to be that segment from where it starts at the vertex where the legs join. Okay? And that altitude, by definition, is perpendicular to the base. And then, special for isosceles triangles. And remember, equilateral triangles are special types of isosceles triangles. So special for isosceles and equilateral triangles. The altitude bisects the base. So we know those 2 segments are congruent. And it bisects the vertex angle. So we know that that angle is congruent to that angle. Okay? So whenever you draw an altitude in from the vertex of an isosceles triangle, you get a lot of information, don't you? You get perpendicular, you get a side that's bisected, and you get an angle that's bisected. We're going to use that. Any questions? All right. Now, knowing the coordinates of a figure in a coordinate plane allows you to explore its properties and draw conclusions about it. Coordinate proofs use figures in the coordinate plane and algebra to prove geometric concepts. The first step in a coordinate proof is placing the figure on the coordinate plane. So this leads us to our learning target, to position and label a triangle for use in a coordinate proof. So here are some guidelines to help you know how to put a triangle on a coordinate plane. It says to use the origin as a vertex or center of the triangle. Quite often we'll position a triangle so that one of the vertices of the triangle is the point 0, 0. Other times we won't do that. 0, 0 might be the midpoint of one of the sides quite often. Okay? Next guideline, place at least one side of a triangle on an axis, especially if it's a right triangle. That works out really well to put one of the sides on an axis. If it's an isosceles triangle, that works really well to put the base on an axis. Okay? Keep the triangle within the first quadrant if possible. You know how your coordinate planes divided up, quadrant 1, 2, 3, 4. You familiar with that numbering? Quadrant 1, if it's not quadrant 1, it tends to be half in quadrant 1, half in quadrant 2. That's what we tend to do. And then use coordinates that make computations as simple as possible. We try to use either just a letter or maybe 2 times a letter. Or maybe for some reason, like if our constant is b, maybe we want to use just b. Maybe it would be better to call it 2b, 3b. Don't do something like 2/3 b minus 7 as a coordinate. You're just making things way too difficult. Now, can all 4 of these little guidelines be used at the same time? Not often. These are just ideas, okay? There are no hard and fast rules on where you have to put a triangle on a coordinate plane to make a coordinate proof. But these are some ideas that will help us. So, let's do a couple of examples. I'm on page 304. We'll start with number 1. It says to position and label each triangle on the coordinate plane, which sounds a whole lot like our learning target, doesn't it? So, they describe the triangle to us. We have a right triangle ABC with legs segment AC and segment AB. Now remember, the legs of a right triangle, those are the 2 sides that connect to form the right angle. They're the 2 sides that are perpendicular to each other. So that segment AC is 2A units long, and leg segment AB is 2B units long. All right, so this is a case where I think I can put 2 sides on an axis, okay? Since I know that it's a right triangle, and I know the legs are perpendicular, if I put one leg along the y-axis and one leg along the x-axis, that guarantees they're perpendicular, doesn't it? So that's what I'm going to try first. Okay, so I'm going to do this. Make your little coordinate plane on your paper. And I'm going to do this. I'm going to put one leg along the y-axis, one leg along the x-axis. And I tried to not make them the exact same length. Since one of them has a length of 2A and one of them has a length of 2B, they're not the same length unless A and B are equal, and we have no reason to think that A and B are equal. Okay? And then draw in the hypotenuse. If the legs are called AC and AB, what's the name of that point right there where they connect? Is it A, B, or C? It's got to be A, doesn't it? What are the coordinates of A? 0, 0. So I will use numbers there. So A has coordinates 0, 0. Now they don't really give us any indication of which other vertex should be B and which one should be C, do they? Okay? So let's just pick this one to be B, just because. And I'll pick this one to be C, because it has to be if I've chosen the other 2 to be A and B. The length of segment AC is 2A units long. All right, so think about this now. Let's get the coordinates of point C. That's what the label means, get the coordinates. Okay, figure out where each point is and try to figure out its coordinates. All right, what's the x-coordinate of point C? It's 0. It's on the y-axis, so its x-coordinate's 0. Now, if the length of segment AC is 2A, that means if I started down here at A and I count up to C, I count up 2A spaces, don't I? So what's the y-coordinate of that point? 2A. And then let's do the same kind of thinking down here to get the coordinates of B. Now this time it's the y-coordinate of B I already know. What's the y-coordinate of B? 0. It's sitting on the x-axis. Its y-coordinate is 0. Now when they tell us that the length of segment AB is 2B, what's the x-coordinate of point B? 2B. We're done. We have positioned and labeled right triangle ABC meeting all those given conditions. We have the length of AB is 2B, the length of AC is 2A. We've got it. Any questions? All right, so we can do that, right? That's a vote of no confidence. Let's try another one. Same directions, position and label. This time we have an isosceles triangle, FGH, with base FG that is 2A units long. Now, I also put our little new information we know about isosceles triangles on here because I'm going to use this, okay? What I'm going to show you, the way I'm going to put this triangle on here is not the only way, but this is a really good way to do this. The base is segment FG. Bases don't have to be the bottom, do they? But isn't it kind of nice to think of it that way? It's kind of intuitively we wish the base always was the bottom. So let's put segment FG on the x-axis. That'll be the bottom of our isosceles triangle. And then there's a couple of ways I could put FG on the x-axis. The way I'm going to do it is this. I'm going to put segment FG on the x-axis in such a way that the point 0, 0 is its midpoint. So I'm going to put F here, then I'm going to go the same amount of space to the other side and put G here, F, G. Now, if this is isosceles triangle FGH, then H needs to be, I can put it up above, I could put it below, but I'm going to put it up above. But here's the thing, I know not exactly where to put H, but I know where H has to go. Well, you just contradict, no, I didn't either. Doesn't H have to be on the y-axis? I don't know how far up or down, but it has to be on the y-axis. How come? Because if I draw, and don't draw this yet, if I draw an altitude from H, it has to be perpendicular to the base. Well, putting H on the y-axis takes care of that. It has to bisect the base. Since I put F and G the same distance apart, I made 0, 0 at the midpoint of FG, takes care of that. And then bisects the vertex angle. Once I draw in the others, you'll see that, yeah, it really does. So, I have options as to how far up the y-axis I want to put H, but H has to be on the y-axis. Does that make sense to you? So I'm going to put H right there, just because I chose. Then draw in the legs. All right, so we've positioned it. Now we need to label it. Let's start with point G. Now, if segment FG has a length of 2A and 0, 0 is its midpoint, think about this. Doesn't that mean to the left of the midpoint to F is a distance of A, and to the right of the midpoint up to G is also a distance of A? That's how you get FG to have a distance of 2A. So if I start at 0, 0, and I go to the right a distance of A, where do I end up? I end up at point G, and that coordinate is A. Does that make sense to you? What's the y coordinate? 0. Now, what's the y coordinate of F? Y'all answered the question I didn't ask. Y coordinate's 0, but you got it though. You didn't fall for it. If I go to the left a distance of A, I don't end up at A again. I end up at a coordinate of negative A, don't I? So, you see how putting the base so that 0, 0 was its midpoint worked out pretty well? It did, didn't it? Okay. Now, H, I know its x-coordinate is 0. And didn't I just arbitrarily decide how far up to put H? So arbitrarily decide a name for that coordinate. Now, don't make a number, make a letter. Because you don't want to say it always has to be 2. It's distance of B, whatever B is. Make sense? Okay. Now, that's not the only way to fulfill those requirements. Okay? And in fact, another way to do it's also fairly simple. Let me see if I can clone that coordinate plane. All right. If I put F here at 0, 0, and I put G down here, excuse me. If I do it this way, what's the x-coordinate of G have to be? Has to be 2A, and the y-coordinate? I keep asking them in the wrong order, and I'm confusing you. I don't mean to do that. All right, does that make sense? Now, there's one place I have to put H. Before, I had to put it on the y-axis. I don't have to put it on the y-axis, but don't I have to make sure that all these conditions are met for an isosceles triangle? So, to make sure that the base gets bisected, what's halfway between 0, 0 and 2A, 0? A, 0, right? So I come here a distance of A, and then that perpendicular line coming up out of there, H has to go on that, doesn't it? So, put H. Now, the x-coordinate of H, before it was 0, what's the x-coordinate of H now? A. And I still get to arbitrarily make up whatever the y-coordinate of H is. Is one way better than the other way? I don't think so. In fact, now that you've seen them both, couldn't you probably do them both? Okay? All right. Now, on 3 and 4, they go ahead and they position it for us. Our chore is to find the missing coordinates. So, for number 3, we have to name the missing coordinates of each triangle. All right, take a look at it and get as much information from the figure as you can. I see that I know the coordinates of point R, they're negative 2A, 0. I know the coordinates of point S, they're 0, B. I don't know either coordinate of point T. What kind of a triangle is this? It's isosceles. That means that right there has to be the midpoint of the base, doesn't it? Because the altitude, which would be the y-axis again, has to bisect that. So look, if from that midpoint to R is a distance of 2a in the negative direction, from that midpoint to T must be 2a in the positive direction. So 2a is the x-coordinate. And what's the y-coordinate? Well, hey, that was even easier than what we did before, wasn't it? Let's try number 4. What are the coordinates? Well, what kind of a triangle is it? Equilateral. And equilaterals are special types of isosceles, so the properties of isosceles apply. The coordinates of W are a piece of cake. What are they? Okay. Now, Z. Let's treat this like an isosceles triangle. Make those the legs. What does the x-coordinate of Z have to equal? Has to be A, doesn't it? Because if that's an x-coordinate of 2a and that's an x-coordinate of 0, that's got to be halfway between them, doesn't it? So, A, is there any certain thing the y-coordinate has to be? So what are you going to call it? I'm going to call it B as well. Now, if I were you, I might be thinking, okay, this is all well and good, and in fact, that's kind of easy. Why are we doing this? Well, we're doing this because we're eventually going to have coordinate proofs. We're not yet. Let me show you what a coordinate proof actually looks like. Okay? On number 5, it says write a coordinate proof to show that triangle FGH is congruent to triangle FDC. So, you can see what I've done here. Using and they've got all the coordinates already on there, so they've already positioned it and labeled it. Okay? Now, to prove that those two triangles are congruent using the coordinates, the only thing I can do with coordinates is find lengths. Right? I can't, as far as proving triangles congruent. I can't find angle measures. Now, I guess I could use vertical angles are congruent, but now I'm not using coordinates anymore. Okay? So to use the coordinates, the way I use them is by finding lengths. So I'm going to try to prove these two triangles are congruent by side, side, side. Look what I've done here. First, find the length of DC. It's right here. I can just do that by subtracting B minus 0, and the length is B. Then I find the length of GH right here. B minus 0, the length is B. There's one pair of congruent sides. Then I'm going to find the length of DF right here with the distance formula. So that's x2 minus x1, quantity squared, y2 minus y1, quantity squared. I'd get A and then square it. Here, B over 2 minus B. I always think of this as 1/2 minus 1. You'd get negative 1/2. So B over 2 minus B, you'd get negative B over 2, which is okay because when I square it, I get a positive B squared over a positive 4, and that's my distance. I do the same thing with GF. Lo and behold, they're equal. There's a second pair of congruent sides. I do the same thing with CF and HF. There's my third pair of congruent sides, and I've proven the two triangles are congruent by side, side, side. And that's what a coordinate proof looks like. Questions? Okay. Here's going to be our assignment. 1 through 5, we've done 5. We just did it together. 7 through 18 and 38 through 41 on page 304.